So, like I said, rigid body motion, that's really important. It's going to go on into the second year as well. It's a very vast subject. We're only going to skim the surface of it. We're going to see the equations, but then the applications are just endless. The idea, and we've already touched upon that, is that you try to generalize what you've seen for one particle to many particles. And then you try to come up with equations that are the same. And the level of difficulty should just be increased a little bit. Yeah, we've seen a lot already. Let's look at this. Say I have n particles. I have an origin here, O, and then I have M1 here, M2 here, M3 here, and so on and so forth. And they each have a position vector, R1, R2, R3, and so on and so forth. Yeah, so we've seen that earlier for one particle. Each particle has a position vector, then a velocity vector, which is the derivative of the position, then acceleration, which is the derivative of the velocity, which is the second derivative of the position. And then each particle is subject to external forces. So for the ith particle, I'll call that Fi, and internal forces. These are the forces that each particle exerts one on another. Think of gravitation, or maybe magnetic forces attracting one particle, attracting one another, gravitation, one particle attracting another, so on and so forth. Right, so those are we call Fij. So Fij, that's the force exerted by the jth particle onto the ith particle. Right, so F12, the force exerted by M2 onto M1, F13, M3 onto M1, and so on and so forth. And then by Newton's third law, you know that the action-reaction, the force exerted by M2 on M1 is going to be the opposite of the force exerted by M1 on M2, which is what I wrote there. Fij is minus Fji. And then, so Fii, F11 is going to be minus F11. The only quantity that does that is 0. So that's why I wrote there, Fii must be 0. Don't exert force on yourself. Okay, so let's try to see where does that lead us in terms of Acquaintance motion. Newton's law. So let's look at one particle first for the IF. So MA, so that's going to be MI T2RI. That's the acceleration of the IF particle, and it's going to be the sum of all the forces that are applied to that particle. So it's going to be the external force, Fi, and then there's going to be the sum of all the internal forces, right? Remembering that Fii is 0. All the other particles exert internal forces on I. Okay? So it seems hard having to solve all those equations. If I have 1,000 particles, do I have to solve 1,000 equations? Too hard. What am I going to do? I'm going to do some maths. What happens if I sum all this? So I'm summing all the equations for each particles. So on the right hand side, I have to sum the external forces, And then I have to sum the internal force. So that's going to be a double sum. Okay, so that looks crazy. But let's just take a second. The first term, sum of all the external forces, we're going to call this F external, the total external force. And the second term, that double sum, let's just expand it. So it starts, I'm going to take I is 1, and then I'm going to sum all the j's. F11 plus F12 plus blah, blah, blah. All the way to F1n. Then I take I equals 2, F21 plus F22 plus blah, 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 F2n, and so on and so forth, all the way to the nth particle. So it's going to be Fn1 plus Fn2 all the way to Fnn. So it's a really long sum, but if I look at it in details, well, first I wrote the Fii's. I needn't have bothered because they're all zeros, right? All those terms, F11, F22. And then I'm left with all the other terms. So if I look here, on the first line I have F12, but that's the opposite of F21. So those two terms are going to cancel out. Then F13 is going to cancel out with F31, etc. F1n is going to cancel out with Fn1, like this. And then F2n is going to cancel out. Oh, my mistake there. These indices should have been Fn2. F2n is going to cancel out with F, etc. Whoa, look at this. All of this is a big fat zero. That's nice. So instead of having to deal with n equations, I could just might be able to deal with all this only. Let's recap. I've just shown, nice maths, dt squared, which is the same as the first derivative of the velocities, which is the same as the sum of all the linear momenta, well, derivative I should say, that's equal to the external force. And in this equation, the internal forces don't play any role. That's the total external force. Nice. Huh. So maybe dealing with just that equation, which is the sum of all the equations of motion, I might be able to solve the problem, at least for rigid bodies. Okay. So let's just write what that is. Pi, remember that's the linear momentum. Linear of the IF particle then I can see I have sum of d dt of the, I can take the dt out. I realize that I have the derivative of the sum of all the PIs. Yeah, I'm going to call that the total linear momentum. MIVI, total momentum of the system of particles. And that's the key. We're going to look at all those particles as a system, not as individual particles. And in many situations, it's really advantageous. We've seen an example already with collisions. Remember, it was advantageous to look at the two, at the momentum of the two particles. If I write this, hence Newton's second law is dp dt That's nice. That's very much like what happens for one particle. The derivative of the momentum is the external force. And then you can note if F external is 0, P is conserved. That's what we did for collision. And that helped us solve the equation for collision. But here we're not going to assume that external forces are 0 in general and see how far we can go. Okay, any questions? I realized because of that time that's stuck at 22, I sometimes go, oh, darn, I'm late. I better hurry now. I only have 10 minutes. No, it's not. That's why I was finishing early. Keep track of that. Okay. So we have the total momentum. And now we're going to go even further in maths. Oh, wait. I'm going far too fast. Oh, yeah. We have to think about test number 2. So this is week 7 now. So we could do it this week, or week 8, or week 9.
When does the next unit start?
The next unit. Yeah, let's have a look. Rigid body motion is pretty long. It's 9 lectures. So I reckon it's not going to be on the test. 9 lectures, that's 2 weeks. That's this week and week 8. Well, unless we do test in week 9. Who wants to do test in week 9 now? Nobody.
So, rigid body motion won't be on the test.
So if we do the test this week or next week, I won't ask for rigid body motion. Or maybe a very simple equation like the one we're just going to do now. You'll see. So, who wants to have test this week? Good. Me neither. Who wants to have test next week? Majority. Who wants to have test week 9? Okay. Week 8 it is. So then, not on Monday because this is just too cramped. So it'll have to be Wednesday, Thursday, or Friday. Any preference? Wants to have it on? Doesn't mind having it on Wednesday. Doesn't mind having it on Thursday. Doesn't mind having it on Friday. Okay, we launch a campaign. Furthest is the best. Michelle might be dead by then. Something will happen. I don't know. Looks like Thursday. Thursday next week. Okay, must remember that now. So if anything comes up, let me know if you want to move it. So the second, well, that's it. Got it. Something I said. They're upset because the test is on Thursday. Are they even taking this course? Okay. Last year I got the best compliment ever. The best. I went to the petrol station, I went to pay, and the guy said, "Hey, you Michelle, right?" I said, "Yeah." Yeah, I took the course, first year primary school with you. I said, "Oh, okay, so how did you do?" "Oh, I didn't do the exam, no, I didn't do it." I said, "Oh, okay, you're repeating?" No, I'm finishing my degree in computer science." I said, "Okay, so how did you move on to second week then, if it's second year, if you didn't do the exam?" So, "Oh no, I didn't have MP 180 in my degree." I said, "Okay, so why did you come?" "Oh, because you were awesome, man." They just took an extra course just so that. Made my day. Imagine that. Okay. So we've seen this dp dt equals, that's pretty much like what happens for one particle. So why not try to see the whole system as one particle, where f external, that's okay, is the sum of all the external forces, and p, capital P, that should be the momentum for one particle. Maybe it's not one of them, it's just a fictional particle. What's the position of that particle? What's the speed? Let's try. What's the mass of that particle? We're going to introduce the total mass. That makes sense. M. Makes sense to talk about the mass of the system. And then we're going to try to write P as something like this, where m is the total mass and v is the velocity of that imaginary particle that represents the whole system. Okay, let's try to do that. So remember that P is like this. Oh yeah, I want to tell you, I forgot to say, the test number 2, I just take short questions from past exam papers and just splice them together. Just to train you for short questions. Remember, in the exam there's 2 parts, 8 to 10 short questions, and then long questions. I can't remember how many there are, so I won't say it. Okay, so it reads like this. MIVI. I want it to read like capital M times V. So I'm just going to multiply and divide by M. That's the same. And then I'm just going to call that's a velocity, yeah? If you look at the dimensions, 1 over m, that's 1 over kilos, and then I have m times v, That's kilos times, so kilos over kilos cancel out, I have a velocity. So I'm just going to call that V. Where V equals 1 over m MIVI. Okay, so the equations of the entire system, all those external forces, all the internal forces, they are the same as if it was just one particle with this velocity and the total mass m. And I don't need to worry about internal forces anymore. Nice, neat. Where is that particle? Well, we can find its position from the velocity, right? Because the velocity is the derivative of the position. So we can find the position of R. It's just going to be this here. MIRI. That's it. And so it's average of all the positions of all the particles. So it's a weighted average, because you multiply the position by the mass, and then you arrive at. So it's a weighted average with respect to the mass and the position. So that position is called the center of mass. This is why in the lecture notes I write Cm as an index here. For here is the message. That's to take home message. That's what we learned today, is that the total momentum of the system is the same as that of a single particle mass m with force. Everything, all 1,000, 10,000, 1 million, 1 billion particles, doesn't matter how they interact one with another. In the end, I end up with Newton's law, as I've seen it before, like this. dp dt is the total external force, where p is the momentum of a fictional particle, but I know where it is, and I know its mass, so I know its momentum. Okay, so you're expected to know how to find the position of the center of mass. Well, I think it's kind of obvious, or at least intuitive, where it should be. It's the average of all the positions weighted with their mass, center of mass. And just to ram it home, we're just going to do an exercise now where you ask to find the center of mass of 3 particles. One is particle m and positioned at 1, 2, 2m at 5, 5, and 10m at 3 minus 1 in the 2D plane. Where is the center of mass? So, yeah, 2, 3, 4, 5. So the first one is here. The second one is at 5, 5. And the third one is here. So center mass, I expect it to be inside that triangle, where I'll let you compute it. This is the formula. And that's a short question that comes up often. That short question okay for the test? What do you think? So you just need to write that formula, but now with those n is 3, right? That's m1, m2, m3. That's r1, r2, r3. Compute the average weighted position. Okay, we do this one together and then we'll have time to do one from a past exam paper. What's the total mass? M plus 2m plus 3m, 6m. Blah. Over 6m. And then I have to first mass is m1 is m, first position I plus 2j, second mass is 2m, second position I plus 5j, third mass is 3m, third position, voila. Then all the m's cancel out, all the i's they add up to 1 plus 10 plus 9, that's 20. All the j's, 2 plus 10, that's 12, minus 3, that's 9. And then that's it. 20 over 6, that's 10 third. 9 over 6, that's 3 halves. So it's somewhere there. 10 third, that's 3 plus the third, 1.5. Is the center of mass. Oh, I forgot to underline RCM. How about that for an easy exercise? Did I go too fast? Just so there's M, so I can cancel the M. And then I just added the i's. 1 plus 10i plus 10 plus 9, that's 20. Then I added the j's. 2 plus 10, that's 12. Minus 3, that's 9. And it actually is often a question in the exams, if you can believe that. Did you watch me? Me talking my jokes? Yeah? Saying jokes. Just ran out. What can I do? No more jokes. Past exam papers. Next look, past exam paper. Let's look at all the short questions now. We should be able to do a good number of them. Okay, last year. No, I can stop the recording now.